Good morning. Welcome to this third day of meeting. It's a pleasure to introduce Yann Brenier. Yann is a veteran of this meeting, and Yann will speak about Monge-Ampère gravitation and optimal transport.
Yeah, actually, okay. It's probably not the right set of slides, but I will because yesterday I spent a lot of time to make it more compact to 18 pages, and now I'm back to 25. So there must have been some mistake yesterday. So I will inflate the talk again. Okay, sorry for this mix. Yeah, so actually, okay, so now I have to readjust completely my brain to that because this is not the right set of slides. Sorry. Okay, anyway, so it's very disturbing because, okay. So then I would like to make a survey of this field, which started more or less at the same time as this workshop in 2000. And the really a key person for that was Uriel Frisch at the Observatoire de Nice. And he is the first one who made the observation that in the problem of cosmological problem of the reconstruction of the primitive universe, of the early universe, this can be set up in the framework of optimal transport using the so-called Zeldovich approximation. And after that, I got very much interested in this problem, and in about 10 years later, in this paper in the Confluentes Mathematici, I introduced what I call Monge-Ampère gravitation, and I will explain how it comes up. And later on, we could do some derivation of this Monge-Ampère gravitation for purely stochastic model of a Brownian clouds. So in some sense, this Monge-Ampère gravitation is a kind of simplification of the Einstein theory, but for this simplified model, we have a completely stochastic derivation in the sense that the gravitation emerges just from pure randomness. Okay, and I think it's quite interesting. And eventually, with Luigi and Emery Barada, we have a decent, rigorous derivation of that. So it's not perfect, totally perfect. And on the other side, at the computational level, there was a big revolution when Quentin Mérigot, that you listened yesterday, made this semi-discrete scheme based on Laguerre cells, which produce really a competitive schemes to compute optimal transportation. And this was followed by Bruno Levy, who have a fantastic solver in 3D. And nowadays, we can do a computation in the Institut d'Astrophysique de Paris with my colleague Roya Mohayai, and with hundreds of millions of particles. You know, so it's really nice. I would have never expected that 15 years ago. So, okay, so now I try to recall. Okay, and so for instance, this is this is a very recent result. You have the preprint on the web with Bruno Levy and Roya Mohayai, and this is a 256 cube particle simulation of the early universe. So it's quite a lot of particles. Okay, and the particle in this framework are what is a particle for this cosmological computation? A particle is a cluster of galaxies. So it's maybe 100 of galaxies. This is a point particle. So the solar system is as relevant for this problem as quarks to solve fluid mechanics, in some sense. So it's completely, I mean, I checked the numbers. The range of scale is absolutely amazing. And so it's very different from the classical Newtonian gravitation. And here, maybe you remember that in the talk of of Quentin, he was mentioning Lager cells. And so, you know, this in this block, you see the numerical simulation is based on Lager cells, in 3D Lager cells. So they look like that. So it means that each particle is mapped to a kind of a small cells by a kind of optimal transportation techniques. So mapping back to the uniform density, because the uniform density plays a role in this theory, in this cosmological theory, and so the Lager cells plays a role of one of these particles, which is a cluster of galaxies. So it's super large-scale computation, and actually there is also some. I mean, they can do also 512 cube, so which. Okay. Okay, and then that's very fresh. Okay, now when I use slides white in black and red, it means that these slides are not so new. I mean, I recycled. When it's blue and red, it's new. So this is a coloring system. Okay, and so as I already told about this this story. So this is the reconstruction of the early universe following the seminal work of Uriel Frisch, which was it's a short paper in Nature in 2002. And the model from people are interested in the equation and PDEs. So you can describe that by this set of equation. So you know, we use A to label the particles, but A in this description is continuous variable. And for some reason, I mean, these people in computational cosmology, they do always space periodic simulation. Anyway, you know, the real ancient equation, you have the propagation of light is, the speed is finite. So in some sense, you cannot observe anyway the whole entire, so it's a reasonable assumption to assume that you have periodicity, although it looks strange at the first glance. And therefore, so we denote by capital X of t the location of each of these particles in time. And the equations are very simple. You have so forget for a second the red terms. So we have the second order derivative in time. The acceleration of each particle is balanced by the gradient of some potential. So it's a little bit like in Newtonian gravitation. So the black terms are really like Newtonian gravitation. And then there is the gravitational potential is coupled to the density rho, which is just, you know, you define the density like this. So at every point you count the number of particles nearby, and this gives you the definition of density. And out of that, you get the gravitational potential, and the gravitational potential is accelerating the particles. However, because of the in this application, this is certainly not the ancient equation. It's just an approximation. So what happens is you derive this model. So this is rather famous people, actually. I think Peebles is a Nobel Prize, actually. So in cosmology, the people, usually they don't solve the Einstein equation. It's too complicated. So they need some approximate model. And so the Newtonian gravity is pretty good, actually, to do that. However, you have to take into account the basic structure of the universe, which is the expanding universe, and this Einstein de Sitter universe. And therefore, this modify the Newton equation by these red terms. So there is some scaling factor. So it's not autonomous with respect to t. You see, it's like an ODE, but it's depending explicitly on t. And there is this factor. Also, there is this very strange factor dx over dt. And here also there is factor t. Yeah, I don't know if Filippo is here because he had a. yeah. So we will skip this discussion. Okay. Anyway, so I mean, Filippo claimed that this is just a matter of change of variable and there is nothing serious about that. But I think I'm not completely agree with this. This has some important consequence because this system is completely degenerate at t0. And t0 is supposed to be the Big Bang. So at t0, you see that the acceleration term is gone. If you assume, of course, that the acceleration stay bounded. And so you are left with a first order dynamics. So it's more like a gradient flow. So it's like a first order equation. And also you see that at time 0, the density should be uniform. And this is very well validated because the observation shows that the primitive universe is almost, it's hard to believe because there is no gap. It's not like now. Now there is a lot of vacuum in the universe. But in the early stage, this is a uniform distribution of matter. So which is hard to be, is much more like a fluid actually. Looks like a fluid of quarks, of particles, but it's certainly not a collection of planets with big gaps. And this has been created by the gravitational effect. The concentration of matter and the formation of gaps is really linked to the gravitation itself. But the early universe is very flat. And also you see that at the early stage, the motion of the particle is the first order, and therefore it looks more like a friction-dominated motion. And this is the basis of the Zeldovich approximation. So I should really be careful about the time because these slides are, it's more and more for 1 hour than 40 minutes. And so this is just like what I said. And then also something really interesting that in Newtonian gravitation, it's a second order equation. So you need to know the position and the velocity of the particle at time 0. Here, no, because the velocity is forced at time 0 to be given by the gradient of the potential. So which means that at each point, you have only one velocity. There is no choice. And so that's totally unusual in some sense. Okay, and yeah, so you see that I have this compatibility condition, so the initial density should be 1. Well, I mean, you can, up to a relabeling, you can assume that the position is given by the identity map, and the velocity is just given by the initial value of the potential, electric potential, which means that actually there is only one data to know, is the initial potential. So in Newtonian gravitation, in principle, you should know the entire field of position and velocity for each particles. And here, no, you just need to know a scalar function. And this is the basis of the idea of Uriel Frisch. He said, well, if we have access to the density of the universe now, what we can see, it's a scalar function, and then we should be able to recover this phi 0, because this is the only thing that you have to recover when you want to reconstruct the early universe. And as I said to you, so I think here okay, this is what I mean. And so, yeah, and so what is so in this framework, there is this really amazing Zeldovich approximation, which looks like a joke, because Zeldovich proposed that a good approximation of this model is just this. That is, the particle, they just move along straight lines according to this initial potential. And you can see that the initial potential, according to the equation, it should be given by, it's the same as prescribing the time derivative of the density. So this is what the physicists call the fluctuation of the density of the early universe. And so since we have no access to T0, we have just access to T is equal to 300,000 years, which is when the universe becomes visible because the photons can emerge from the soup, the original soup. the universe is totally obscure and opaque until 300,000 300,000 years, where the photons were able to escape, and we receive them now from almost 10 billion years. And the fluctuation is very small, so it's like 10 to the minus 4. So the universe is really almost homogeneous. And therefore, it's very important for physicists to try to recover this phi zero. And so it's an inverse problem. So we know we can observe the density, and, and then we want to recover the phi zero. And Zeldovich proposed a completely stupid model that the particles just move in straight line. So it look at control. And of course, this is reminiscent of the story of Lucretius, where to describe the universe, you say, well, these particles are just moving in straight line, and from time to time there is some fluctuation, and this and so I think I showed you that many times already. So just to show how good I am in Latin, and so you have I know in Italy, so many people have learned Latin in a very serious way, and so this is fantastically similar to this Zeldovich idea. I'm still fascinated by that, so each time I show it. Okay, although I had canceled that in the short version that you don't see. Maybe I could tell you, oh yeah, this slide has been canceled. This is a cancel culture. Okay. So now what is Monge-Ampère gravitation? So this is my input in 2011, and I presented that already here. I'm pretty sure I didn't recover the slides, but I'm sure that I told you that to the oldest people among us. And the idea is very simple. So this is the Peebles model. And of course, 1 plus t Laplacian of phi looks very much like the expansion of the determinant. So this is just the expansion of the determinant of the identity plus t times the Hessian, and you just take the two first terms. Okay, and in 3D we have two additional terms that we neglect. And so this was this is the idea, the definition of Monge-Ampère gravitation. It's just this modification. And so there are good reasons to do that. Oh, sorry, because actually, yeah, there is no modification if you have just one space dimension dependence on phi, because the determinant is the same as it's clear. Now, well, it's not so bad as an approximation, because when t is close to 0, and the field is very small. As I told you, the initial phi 0 is extremely small. So it's certainly a good approximation at the early stage of the universe. And so this is what I love, that actually it's a very nice exercise in optimal transport. So if you are really very trained in optimal transport, you should be able to do the computation in few nanoseconds, maybe. Okay, is the fact that if you make this modification, so the Zeldovich approximation is correct, because thanks to this by some optimal transport reasoning, you see that the trajectories are exactly the ones that are optimally move the uniform density to rho. And it turns out that you cancel both separately this term. So you get d2x, dt2 is 0, and this term also. And this is like the gradient flow of the square Wasserstein distance or something like that. Okay, and therefore you recover Zeldovich. And this also explains why the method proposed by Frisch works pretty well, because in some sense it solved the optimal transportation problem. Just to recover phi 0 is the Kantorovich potential. So the phi 0 is just the Kantorovich potential of the problem of moving the uniform density to the density that you can observe. So that was a brilliant idea of Uriel. And also, I mean, this is much more like a conjecture that in some sense, I had the feeling that in some sense the Einstein equation is related to geometry. Of course, we reach curvature, but Monge-Ampère equation is also related to geometry, because you know that when the Minkowski solved the so-called Minkowski problem, this is like recovering a convex surface out of the Gaussian curvature. You know, if you know the Gaussian curvature of a convex surface, you can recover it essentially uniquely. And therefore, this is almost the same problem as the optimal transport problem. It's very similar. So I like this idea. So I still think that the Monge-Ampère, the Monge-Ampère gravitation could be derived quite directly from the Einstein equation without passing through the Newtonian approximation. But it's I don't know how to do it actually. Okay, and actually one of the young guy in the Institut Astrophysique de Paris, well, I shouldn't talk too much about that, but he discovered in the literature of general relativity the concept of Galileons. So it's a funny name. It's like Galileo. So we are in the city where Galileo was born, right? The Galileons. And the Galileons are a little bit like a Hessian equation. It's related to the Hessian equation. I think it's a very interesting field to study. Because you look at all the equations you can generate with the minor of the Hessian matrix. And this is used by some people in general relativity, and in some sense, Monge-Ampère gravitation can be put in could be put in this framework. So there is some hope to make progress on the derivation of the equation from the Einstein equation, in my opinion. Okay, but it's largely open. And okay, so I don't know if it's. I think this is the only time where Quentin appears in the lecture. So I hope you can see it. So of course, in terms of numerics, the Merigo evolution makes the computation of this problem reasonably good in the sense that it's more expensive than solving the Poisson equation, but it's like it's maybe 10 times more expensive. And you can put it's scale the same. So this is why we can do hundreds of millions of particles. And once again, the 3D version of Merigo's algorithm is due to Bruno Levy, and who is a fantastic computer guy. Okay, so this is the same picture that you saw already. And now, in this second part, I would like to discuss the connection with between the Monge-Ampère gravitation and Brownian clouds. So in some sense, to see as I said already, that Monge-Ampère gravitation has emerging from the purely stochastic model of a Brownian cloud. And in between, there is Euler. And you know that I'm a big worshipper of Euler. So I am thinking about starting a new religion based on the worshipping Euler. And then we can, Euler was born in Basel, so we can put the money in Switzerland. So I think it's very good. So okay, the discussion is very much related to this nice picture that I saw in the Big Bang Theory, a very good program. And you see that's a melting Rubik's Cube. It's a combination of combinatorics to fluids. Fantastic. It's exactly what the purpose of what I'm going to say. Okay. So this has been censored in the short version. So so I try to be very quick here. So you may know, I mean, it's pretty well known that the Euler equation for incompressible fluids has a very nice geometric interpretation. So geometry is here again, because he understood that Vladimir Arnold understood that the Euler equation just described geodesics along the group of volume preserving diffeomorphism. Okay, so this is what I said. So you have let's say, to make the discussion simpler, you have a domain in RD, or maybe the flat torus, and you look at all incompressible maps, and you put some L2 metric on that. And you compute the shortest path according to the L2 metric, and this gives you the optimality equation are just the Euler equation of incompressible fluid. Okay, so for instance, if I put myself on the two torus, and I have three diffeomorphism, and only one is volume preserving. So since we are in 2D, volume preserving means area preserving. And so if you fail that, it's very bad. So you should guess which one is which area preserving. Okay, so I don't want to humiliate you. Of course, this one is the only one. So it's a very severe constraint to be area preserving. So following a geodesics on this set is a very strong constraint. So it means that you have you cannot go in straight line. And what is making you a geodesic curve is the pressure gradient. So the pressure in the incompressible model is just a way to stay on the manifold of volume preserving map. And at the early stage, I think it's a long time ago, it's even making this, it is the way I started. I mean, optimal transportation, I started because of this idea that we should be able to do incompressible fluid mechanics with permutation. Because volume preserving maps at the discrete level are permutation. So I said, and I think it's as early as maybe I think the idea came up 86, I think, 1986, right after Chernobyl. So maybe this was some kind of but I was in California, so I was quite away from the contamination. Maybe my brain was affected by that. So then, and then of course, you know, these classical games that in French we call the taquin, where you can do motion by permuting blocks. So this is the same idea. So I can write a kind of approximate model for incompressible fluid in the following way. So let me consider a domain to be the unit cube, and I have a finite number of particles. And I would like the finite number of particles to be essentially volume preserving. But of course, because there is a finite number, you cannot do a smooth motion and to be a permutation at the same time. So either you make the time discrete, which was my first idea, but there is another way which is quite interesting, is to use a penalty method. So you relax the volume preserving constraint by just putting a penalty potential. And this penalty potential is like a Wasserstein distance in some sense, because you look at the distance between the cloud of points to the lattice, which I denote by capital A of alpha. So you have the lattice which substitute for the uniform density. So it's reminiscent of this work of Ambrosio Trevisan about the comparison with the discrete measure and the uniform measure. And you put an epsilon. So in some sense, this is the kinetic term, and there is a penalty to be far from the set of the grid points up to a permutation. So this is very important to have the permutation group here. Okay. And then, well, strictly speaking, I don't think that anyone has really proven, well, I mean, it should be doable to do that. This is a good approximation to Euler, but at the level of theoretical physics, it's absolutely obvious that this is a good approximation to Euler. It's consistent with Euler. Okay. And actually, if you this penalty method for geodesics has been known for a long while for smooth manifold, and I found a paper of Rubin and Ungar in CPM 1957. Great year. Okay, so out of this, so this is the action principle. So as physicists like to do, we derive the equation out of that. And so we do calculus of variation. I mean, this is a good place to do it. Okay, and then out of that, you get this dynamical system, which looks very appealing because it's supposed to substitute for Newtonian gravitation, but here there is no green function and there is no interaction. Particles are interacting only with one of the grid points by optimal assignments. So actually, the dynamical system really like that. So you have second derivative is given by this kind of anti-repulsive force, actually. Very simple to compute, minus the grid point you are, which is the closest to you in this sense. That is, you look at all the points together and you find the best assignments between the point and the grid point. So which is like discrete optimal transport, quadratic discrete optimal transport. And then, at least at the formal level, it's very easy to pass to the limit, to the continuous limit, and by kind of folklore optimal transportation calculus, you recover exactly the Monge-Ampère gravitation this way. Because this is like a discrete optimal transport problem. So this is a way, at the continuous level, you recover this. And then out of that, you recover the gradient of the potential, which is accelerating the particle. Okay. So we made this connection between the Euler gravitation and of course, here, for instance, I am drifting a little bit away from the early universe because this doesn't include the Big Bang terms. So in some sense, you have to adjust the theory to the early universe technique. So the early universe technique was a pretext to get Monge-Ampère, but now we forget about the early universe and you concentrate on this model. Okay. Now this is blue, so it's newer. Okay, it's a newer slide. And so in some sense, we just saw that at the discrete level, the Monge-Ampère gravitation can be described in this way. So keep in mind this kind of formula. So once again, maybe the notation, capital of A is the lattice point. And you have the sigma, which is the optimal assignment permutation for linking the position of the particle to the lattice. Okay. And then actually, eventually we had so I got a formal derivation long time ago, actually 8 years ago, of these from the Brownian clouds. And there was 2 levels of large deviation theory, but one level was difficult because large deviation necessitates some smoothness. So later on, I got the idea of reversing the limiting process, and by using I skip the details, but using what some people call the onde pilote after Louis de Broglie, which is a way of which was introduced by de Broglie to describe quantum particles, not by Brownian motion as it is often done, but by following the so-called osmotic velocity. So you look at the wave function, you look at the density attached to the wave function, the square of the wave function, and you look at the logarithm of that and the gradient of the logarithm of this. And this gives the osmotic velocity field. So it's a smooth field, and you follow the particle like that. So this is the Louis de Broglie idea, and I think it's a very interesting idea. And by using this step of this de Broglie step, we can skip one of the problem issued by the large deviation principle, and after that, we have a more reasonable large deviation problem for non-very smooth field. And thanks to Luigi, actually, this was an output of the meeting in Lyon, where you were awarded the doctorat honoris causa. And so I think Luigi gave the idea very quickly. And then it took a lot of time because of me to publish a paper. So I can say, oh, it's very recent work, but actually it's pretty old, but it took a long time to write down. And this has been published 2 years ago. Okay, and this can be explained by this nice drawing, which is taken from this paper with Bruno Levy, and Bruno made this beautiful picture, so I couldn't do it on the computer. And so explains that. So the idea of, it's not the proof, of course. So you have the Brownian clouds is just a collection of particles completely independent and indistinguishable, which have the same volatility, So they are just moving together. Absolutely no interaction, zero interaction. However, when they move according to Brownian curves, as an observer, you have no access to their identity. You don't know who is who. So you just access to the distribution of them. And so the problem, so who is coming from where? So for instance, is this guy coming from there or is this guy coming from that? And by a large deviation theory, there is an answer to that. So the in the zero so it's a kind of conditional problem. So you have some observation of a Brownian. It's very unlikely that you can reach this configuration with Brownian motion. So if you try to run on a computer Brownian motion, you will never get anything. So it's really extremely strongly sorry? Yes, absolutely. I'm just rephrasing the Schrödinger problem. Absolutely, you're absolutely all right. And therefore, in the vanishing noise limit, what you observe is that actually the particle not only they move according to geodesics, which is expectable from the Brownian motion, but the assignment is automatically given by the optimal transportation strategy. So the labeling, so in some sense, it's a little bit, it's very good for countries like maybe for the Chinese Communist Party. You can in the crowd you can know who is who. You know, so you have the riots here, and then you can really get with a good accuracy. So it's very practical application. Okay, and you get this. And so out of that, you get the Monge-Ampère gravitation. So of course, there is some work to do that. Okay. And yeah, oh yeah, I completely messed up the timing. Okay. So I would like to, because I already told 2 years ago, I mentioned this approach of looking at I'm skipping now Monge-Ampère equation, and I want to do something about Einstein equation. And I gave a lecture on this subject 2 years ago here, in this very room actually. And there has been some very slow progress in 2 years, unfortunately. However, I would like to give you. Okay, so I know I can cancel this one, so I can go directly to this one. And so you don't need to know too much on gravitation, but so the basic idea that I use is you use this Christoffel symbol, and you lift the x is a space-time variable, and you lift the problem to the tangent bundle. And actually, Robert McCann, at that time, I used it was the phase space, but actually phase space is a cotangent bundle. And as Robert corrected me, it was right. So this is the tangent bundle. So psi is a tangent vector. It's not a cotangent vector. So you do this lifting of the Christoffel symbol, and it turns out that because I have only 2 or 3 minutes, okay, 5 minutes including questions, so it's very short. So it turns out that in this vocabulary, the Riemann curvature is extremely easy to remember, because it's a kind of it's a kind of curl with a kind of Lie derivation. So it's very easy to remember. So so I cannot give you the details. So you get the Ricci curvature is just contraction. So it's more obscure. So this formula is much more obscure than obscure for the full Riemann tensor. Is very easy to remember in terms of it's a very simple commutator to compute. And the Einstein equation with cosmological constant in vacuum just means that this guy is proportional to the metric JKM with a constant, which is called the cosmological constant. Okay, and it turns out that this is the relationship between the metric and the Christoffel symbol. Okay. Wow, so if you never saw that before, it looks really horrible. However, if you do, it boils down to this very simple equation, which looks like a continuity equation, where in classical fluid mechanics. And to do that, you just introduce this function rho, which is like a tangent bundle density, which is like a Gaussian structure with respect to psi, with the weight given by the metric, and there is a factor depending on the index. Okay, and now again we use this definition, and out of that, simple calculus give you this formula. Oh, it doesn't matter. Ah, yeah, okay. But if you see that, for instance, if you take Gij with the +1 for the time and -1 for the space, it's not so bad because it's blowing up only on time, and you can say that the time is a finite interval. That's a good idea, actually. Time is. And actually, you can use the classical continuum mechanics notation because these are flat gradients. It's Euclidean gradients. There is no geometry in this equation, just flat gradients in the tangent bundle of R4, so R8. And we can rewrite also the Ricci is equal to lambda G in this way. So we have the gradient in X of this quantity is balanced by the divergence of this quantity. So in this notation, all is a flat gradient, no geometry. And the brackets here just mean that you take a matrix and you remove the trace times the identity. It's not the deviator, like there is no factor 1 over d, but this is this formula. The bracket of M is M minus I4, and 4-dimension trace of M. Yeah, and in this, yeah. Well, yes and no, but actually, yeah, if everything is in 4-dimension, yes, you're right. And so, the time is almost over. And this is really strikingly similar to Euler equation for compressible. So I mentioned Euler for incompressible fluid, but Euler in the same paper, he also addressed the compressible case. And so if you take the isothermal gas, which means that the pressure is proportional to the density, and the factor of proportional is a constant speed of sound. C is not the speed of light, it's the speed of sound. And in the isothermal model, the speed of sound is constant. And now you have a dictionary between the classical variable in continuum mechanics, time and space. So now the time becomes the time-space variable. Psi is in the tangent space. So the derivatives are more or less the same. And the c square, the square of the speed of sound, becomes minus the cosmological constant. So in some sense, it's... Sorry? Yeah. That's right. And so on the Euler side, you have this congestion model. You reverse also the sign of you have an imaginary speed of sound, and this is related to congestion models. So you can ask Filippo, for instance. He's very good in congestion model, right? Okay, so okay, and then we are back to Euler. Yeah. So in the new version, I put Euler encore, because encore. Okay. And yeah, so I think I should skip that. So, okay, so far I have not been able to do anything really serious about that, but I have some hope to do, actually, yeah, maybe I can just show the formula. It's complicated, but for the isothermal Euler equation, there is, you can do a kind of optimal transport version of it, a ballistic optimal transport version of it, with a beautiful formula, I think, not so known. And then the idea would be to lift this formula at the Einstein level, but there are some difficulty to do it. So I don't know exactly. But this is one of my favorite vision. And sorry, I'm already late, even without Even without caution, I'm late, sorry.
Thank you, Jan. We have
Right,
time.
I forgot to thank, of course, the organizer. It's a fantastic place to be.
We have time for some question. Please.
Just a comment concerning the first part of your talk with this early universe. This same picture from a fridge paper appears in my paper on this entropic measure. And I was also in contact with fridge because there's really a strong symmetry or a strong similarity between this explicit construction of entropic measure with his cells and his picture, which is of course which started with a different point process, but essentially it's indeed, as you described, transporting this inverse map from the Lebec to the point.
Yes, yeah. Thank you for this comment. Yes.
Okay, we are ready for the second talk given by Simone Di Marino from University of Genova. And Simone will speak about the ground state energy is not always convex in the number of electrons.
Thank you very much. So from the title, it's not apparent that it's an optimal transport stuff, but we will arrive to that. And actually, so thanks to the organizers for inviting me here. And I talk about this also because I think my first time that I attended this conference, there was Paola Gori-Giorgi that was talking about something like this, and I worked on several directions, and then this is one of the last thing that we have done, and I think it's very nice because it's really something which is now an application of optimal transport theory to this field, I guess. So I will start recalling precisely what is the ground state energy, what I mean in particular by density functional theory. So, introduction. And this is a joint work with Luca Nenna, which is in Paris, and Mathieu Levine, which is also in Paris. So, what is the ground state energy of an electronic system? So the idea is that we have n electrons, and this n will pop up a bit everywhere. And so now here we are describing psi, which is the wave function associated to these n electrons, and they are immersed in a field. So we have a potential energy, which is an external energy, which is felt by the electrons. And these three contributions are the kinetic energy of the n electrons, which is just the gradient psi squared. And here I put an epsilon because usually it's h bar divided by 2. This will not really matter for us, so we will tend epsilon to 0 then. But this is the kinetic energy. Then this second term is the potential energy coming from electron-electron interaction. Okay, so this is inside this wave function. Wave function describes all the n electrons, and this is the internal, if you want, the internal potential energy. Instead, this is coming from an external energy. So every electron feels the same potential, which is usually coming from protons, let's say. So we have a molecule which is fixed, and we want to understand what is the electronic structure of this molecule, what is the ground state. We are just interested in the ground state, so we state just the minimizer. Usually in chemistry, they are interested in all the levels, and so you're solving actually not this problem, but you're looking at the Hamiltonian and the eigenstates, etc. We are just interested in ground states. Okay, and the conjecture, which has been popped up in the literature several times, is that the energy, this energy, which depends on the number of electrons and the potential V, is actually convex in n, okay, in the number of electrons. Yes? Yeah, so the subscript A is just that this is anti-symmetric wave functions, because the electrons are actually fermions, so by Pauli exclusion principle, you need the wave function to be anti-symmetric. This actually, for us, will not play the role, but at the beginning, we'll see that for the FT, going to optimal transport is important. Okay, so now I will try to explain in the next slide why, what does it mean that is convex and why we should expect it to be convex. Okay, so this is the example. For example, this is numerical, or no, this is by evidence, by experiments. The case of the energy of the oxygen atom. Okay, so the oxygen atom is just, let's say, 0.8, meaning that there is just, you know, the nucleus of the oxygen has 8 charges, and so the potential which is felt by every electron is just minus 8 over x. Okay, so with this potential, now for every n, we can try and minimize this thing, or we can really try to do the experiment and just put 1 electron, 2 electrons, 3 electrons, and see the energy, right? And so for when n is larger than 9, usually, so there is for every potential there is a cap for which you cannot bind more than some electrons. So if you try to bind another electron, then it escapes away because the repulsion of the electrons becomes stronger than the attraction of the nuclei. So the variational problem is not actually a mean, it's an inf, because yeah. Then in the infimum, this infimum becomes constant from some point on, and actually there are estimates by, I guess the first one was Lib, but then the most used one is by Lyons. Which estimate, I guess, now I don't remember if it was, you know, if you have the sum of these, you sum them up for every nuclei that you have, is the sum of that plus the number of atoms, and this is the maximum number of electrons that you can bind. An estimate, of course. Okay. So what we can expect is that actually the energy is always decreasing, otherwise you spit out the electron, as I was saying. And energy gaps, these energy gaps, so what is convexity in 1D is just that these gaps are getting smaller and smaller, right? The energy gaps can be thought as what is the energy that I require. So once I have 8 electrons, what is the energy that I need to exert it on the electron to extract it from the nucleus? Okay, the last electron. And so the energy that are needed to take away an electron, the 8th electron, the 7th electron, etc., etc. So we are saying that the energy that we need to extract every electron increases as I'm going into the core. So convexity, it can be thought as the inner electrons are more tightly bound to the nucleus, which is something that is expected. Yes? Yeah, okay. So there should be spin also, but again, it doesn't play a role. Also because, so we'll see that actually all the computation that we will do is actually we will do with epsilon, which is 0. So there is no kinetic energy. So no, we forget about Pauli principle basically, because you don't have, so anti-symmetry and symmetry are the same. Okay, well, don't worry. Maybe it will be clear at the end. We will be clear at the end because the nuclei that we will have actually will have a very small charge, so they can have just 1 electron. So it's not important to have you know, Pauli principle, exclusion, spin, etc. Okay. So this is the, as I was saying. Okay, we just reviewed this, and now in order to put it in a different way, so giving another equivalent definition for this convexity, we introduced the grand canonical case for the minimal energy. So what is the grand canonical ensemble, usually in physics, in statistical physics, is that we are not requiring that the number of electron is fixed. What do I mean by that? If you remember, usually when you have the wave function, what can we think as the wave function? Okay, the wave function gives us the probability, right? The square of the wave function is the density of the probability of finding the electrons in that configuration. Okay, the n electrons in that configuration, right? Now, in the grand canonical ensemble, the idea is that we still have these configurations available, but we also can let not only the position varies, but also the number of electrons varies, right? And this is usual. So the main example that you can think of is the subsystems. So let me draw just a picture like this. So imagine that you have two a nucleus here with two protons and the nuclei here with one proton, and maybe you have just 2 electrons to put in this system, okay? And now these electrons will do something like this, okay? And now, if you restrict yourself to looking at this subsystem, okay, in this subsystem, probably there won't be always 1 electron or 2 electrons, right? So there will be a probability which is non-negative, strictly positive but less than 1 probability of having 1 electron, and a strictly positive but less than 1 probability of having 2 electrons. Okay, this is the classical. Also, you can do it also in classical statistical physics, when you have 2 boxes which are connected by a very narrow neck, and you have n plus m particles here, but then you have some probability that the particles here comes here and the particle here come here. But maybe you are just interested on this subsystem, so you don't have anymore a fixed number of n, but it can oscillate a bit. Now this depends, of course, on the how narrow is the neck, but you can do something like this, and this is called grand canonical systems, when also the number of particles can vary. And so we can write this down. We can write this down, and we have this additional probability, which is the probability of having an electron. Of course, the sum of the probabilities should be 1. And then we have, for every probability, we have a wave function. For every n, we have a wave function. And then we fix the average number of particles here. Okay? Again, you think here, maybe here we have an average particle number, which is 1.5, maybe 1.2. Okay? And then you try to understand maybe what is the best lambda here. But maybe it's 1, maybe it's 2, but you can have 1, 2, or 3 particles. I don't know, something like that. Okay, so you fix the average number of particles, and then here you have the probability, and there you have wave function. And then you minimize, and this is the energy for every n, right? So the energy of this wave function. Okay, and now it is, of course, almost clear, almost evident that this grand canonical energy is actually the convex envelope of E and V with respect to n. Okay, so if we come back here, you see, so E and V is just these points, and now the EGC lambda is actually the line depicted in blue. Okay, and of course, now this convexity of E and V is equivalent to the equality E equals to EGC on the integer points. Because, of course, E is just defined on integer points. This is defined everywhere, but it's sufficient to check it on the integer points. So convexity is equivalent to the equality between canonical and grand canonical. Okay, so you have question up to now? This is the statement of the conjecture, if you want. Now we pass to the technical stuff in some sense, which will have some optimal transport flavor. So let me check also the hour. Okay. Okay. So the density functional theory is a way that was started by Hohenberg and Kohn to try and find this ground state in a smart way. What do I mean by a smart way? Well, let me rewrite the problem. So the problem here is that, okay, this is a minimization problem, but the space on which we are minimizing, it's a pretty huge space. Even if we are doing oxygen or something like that, it's R to the 24. So if we discretize R with, I don't know, 10 points, it's already 10 to the 24 grid, and so it's unfeasible. And so actually chemists and physicists came up with several approximations of this guy, because it's the most important thing that they have to compute. What Hohenberg and Kohn did is an exact reformulation, okay? An exact reformulation, not an approximation, which is based on this density functional, which will be something which is depending only on the one electron density. What is the one electron density, which I defined here, is just the probability of having one electron of my n electrons in some specific point, right? So what do I have to do? I take the wave function of n electrons, I integrate out all the other electrons, and this will be the probability of finding one electron in X. And usually, in mathematical physics machinery, this is not normalized to be a probability measure, but we multiply by n, taking into account the fact that there are n electrons. Okay. In this way, this will be more agile when we pass to grand canonical, because then this is just a measure with mass n lambda or something like that. Okay. And so the idea of Hohenberg and Kohn is to minimize, we do this bi-level optimization, if you want, not bi-level optimization, but we separate this minimum into two min. So I first minimized among all these psi, which give the same one electron density, and then I minimize on the one electron density, right? Pretty simple. So this is, of course, the same problem. Now, what is the very nice thing is that this term here actually depends on only on rho, because if you recall, this is just separable. This is the sum of v of xi, and so it depends just on the one electron density, because it's not the interaction. It's the interaction between one electron and the external field. Yes. Yeah. Yeah. X. Okay. In this case, X do not have a heavy notation. This is X1, X2, Xn. Is different from the X here, but it's the same of the X here, because Vx is just the sum of separables. Yeah, it's different from this one. Right, thank you. Okay, so now this splits into this part and this part here, right? And now we give a name to this one, and this is what is called the Hohenberg and Kohn functional. Here I wrote LL because what we will use actually is the Levi functional. The Levi functional is simply the convexification of these with respect to rho, okay? But it's the same in the effect of looking for the minimizers here. Actually, this is the same. If you put Hohenberg, Kohn, or Levi-Lib, you get the same energy. Yes. Yeah, convex hull with respect to rho. Yeah. Okay. So what is the benefit of this? So the benefit of this is now that the very nice thing is that now this is what is called the universal density functional. It doesn't depend on V. It's universal. It depends only on N, right? Implicitly, and on the interaction between the electrons, which is always the same, right? So it doesn't depend on V, and all the dependence on V is here. And so this is a universal thing that one can try to study in generality. And so all the effort that goes there automatically goes to every E and V that we want to compute, right? Because then you see here that actually E and V is the Legendre dual of minus F LL rho, because this is the linear functional and then plus, but okay. These are actually dual one to each other. E will be concave in V. This is convex in rho, and they are dual of each other. So we can recover E from F and F from E. Okay. And so what has been the optimal transport community dealing with is actually this little guy here in the limit when epsilon goes to 0, right? So we do the what is called the semi-classical limit. So we take epsilon and go to 0. And what is the limit of this guy here? Well, you don't have any more this. It remains just the integral of VEE and then this psi squared dx. But this condition is just having this measure having the marginal, the one marginal, which is rho. And then since psi is anti-symmetric, this is symmetric. So if I have one marginal which is rho, every marginal is rho. So I have all the marginals which are rho, actually rho divided by n, if we want to speak from the optimal transport perspective. And so we can show that actually epsilon, which epsilon that goes to 0, this problem converges to this optimal transport, multi-marginal optimal transport problem. So we minimize among all the probability measure which have marginals, which is rho divided by n, and we minimize this VEEX, which is now a cost function of n marginals, right? So I mean all these people, which is not me. So at the beginning in 2012, there was a couple of papers by Kotar-Friesel, Kruppenberg, and Buttazzo, De Pascal, and Gori-Giorgi, where they proved this convergence for the bosonic case and the fermionic case for n equals 2 by Gero and his collaborator. And instead, Buttazzo, De Pascal, and Gori-Giorgi, they studied actually the limit functional, looking for also explicit solutions in the 1D case, and doing also a bit of duality, etc. So these were the first ones doing really the mathematical work. There were other papers by Gori-Giorgi and collaborators, which were more like, okay, we expect something like this, but without any proofs. And then, so in this line, so as Robert was pointing out, these actually they are anti-symmetric, so it's a bit more tricky to get actually the antisymmetry. So the antisymmetry is the fermionic case. The symmetric is the bosonic case. So in order to get actually the antisymmetric, we needed to take time. And so there was a paper by De Pascal and Bidini where they did 3 and 4 electrons for the fermionic case. Then Mathieu did for any n fermionic case, but this Levi-Lib functional, so which is a relaxed functional. And then in the end, again, Gero with Codina and Claudia, they did for any n actually the fermionic case directly, so really the Hohenberg-Cohn function. Okay, so this is for just the limit as epsilon that goes to 0. What about the grand canonical? So of course you can do all the same, and the grand canonical DFT will be what I've written here. So it's just the convex combination again. And again, as epsilon goes to 0, we expect that something like this happens, right? So we expect that this actually converts to this. And actually, while I was writing it, I said, okay, actually nobody did this this limit, we actually studied it, this one, and for the paper, for the counter example, we have an ad hoc argument for the potential that we need that shows actually that this is very close. Sorry? Sorry, yeah, the Pn is again the probability of having n electrons, because now the number of electrons is not fixed. Okay, you can have 1, 2, or 3 electrons, 0 electrons. There can be a case in which you have 0 electrons. Okay. And this problem actually was introduced, so this problem here was already introduced by Levin, Liebe, Seringer, and Kotar and Petrake in around 2015-16 in order to study actually the asymptotic expansion of actually dysfunctional when the number of electrons goes to infinity. Okay, so there is an asymptotic expansion, and in order to do the correct calculation, you need to introduce this one to do some kind of subadditivity formula. And then we studied it, and now we just published the paper where we study in full this problem in general. And a similar version was studied by Bouchité, Buttazzo, Champions, and De Pascale in 2020, and then by Bindini and Champions in 2023. The difference from this one and ours is that, so we studied with a bit more generality, and the key difference is that we allow the number of electrons to be any. Instead, these two papers, they have the restriction that n is greater or equal than 0, but less or equal than some big N. Okay, so there is a restriction of the maximal number of electrons. And this actually plays a role in our analysis. So now I will switch through grand canonical OT, old and new, meaning that, of course, this is still an optimal transport problem, so there are many properties to be expected as in the classical OT. What is the new? So what is something different that happens in the grand canonical? Well, so in general, so we have to prescribe a family of costs now, right? So for every n, we have a cost, and they have to be, I don't know, they have to talk to each other in some sense. So we try to do it as general as possible. So this is really a family of multi-marginal costs. Then for every row, we can consider this, which is just the generalization for any cost of what I've written before. And again, what are we interested about when we are looking at this problem? The usual suspects. What are the usual suspects? Existence of minimizers, continuity with respect to row in this case, duality, so if there is a dual, and support of the minimizers. I write it like this because it is the best way then to describe. So support of the minimizer is the usual thing that one tries to do when I have, I don't know, also two marginals. I want to see if the support of the minimizer is lower dimensional. Maybe is really on the graph of a map or something like that, right? In this case, this will assume a different meaning, but we'll see just in a bit. Okay, so I won't talk about continuity and duality, which are a bit more technical, but they are more or less the same of what happens in classical OT. I will focus on the existence of minimizer and the support of minimizers. So the existence of minimizer is not as for free as for the classical OT. What is the problem? The problem is that the support actually it goes to infinity. It can go to infinity. Sorry, the Pn, so the number of electrons can go to infinity. So we need some hypotheses on the costs that let us see that actually we have some bounds, so some coercivity in these probability measures, basically. Okay, and this is actually there are these two notions which are new in the optimal transport jargon, but they are not so new in the physical, mathematical physics literature. So, and there is stability and superstability. So what we are saying, so stability is just saying that Cn, so these costs, are bounded from below, okay? Which is fair. Bounded from below with something which is linear in n. So why this is needed? This is needed just if you plug it in for any gamma which is admissible. This is just saying, okay, actually the functional is bounded from below. If I don't have something like this, if this goes like n squared, then I can put all the mass with n very big, and then it goes to minus infinity. So this is stability, which is the minimum requirement to have at least that the energy is not minus infinity. And then there is superstability, and superstability is the one that actually gets us the coercivity. And so what we are saying here, this is very complicated, but it's actually pretty simple. We are saying that for any compact set, right? For any compact set, there cannot be too much particles in that compact set. Why? Because if there are too many, then this becomes large. This is counting the number of electrons which are in K. But if this is too large, then this squared maybe beats this minus n over epsilon K. So for every compact set, there cannot be more than big O of n. So there should be little o of n for every compact K. But this is for every compact, so this gives us also actually coercivity, because by covering we can show that actually the Pn as probabilities on n are tight. Okay. Sorry? Coulomb, of course, satisfies this. So whenever you have a pairwise interaction where the cost is positive, actually you need just greater or equal than 0, I guess. No, maybe be positive, yeah. If you have a pairwise cost which is positive, then this is granted. Yes. Yeah, exactly. Yeah. If you have attraction, so this is this is what is taking place, in the interaction between electrons. Of course, if you have attraction between electrons, you put as many electrons as you want, and you go to minus infinity. So, yeah. Lennard-Jones works. Lennard-Jones works because Lennard-Jones works because the main classes, let me say, the main classes for which this works are the positive ones and the ones which have a Fourier transform which is positive. Right? The classical in the convex positive sense. I don't remember what is the name, but Lennard-Jones is a sum of a positive and something which has the Fourier transforms which is positive. So Lennard-Jones is fine. Thank you for the question. But for example, Lennard-Jones doesn't work for the continuity. It's not semi-continuous because you can take two electrons which are at the right distance, which is negative, which has a negative interaction. You can put them at plus infinity, and then the energy jumps up. So it's not Lauer semi-continuous for weak convergence. But it will be always Lauer semi-continuous for tight convergence. Okay. And the theorem is that actually existence of the plans holds under superstability. And we have, of course, examples, trivial examples, if you wish, where if superstability doesn't hold, then you don't have existence, because particles are escaping at plus infinity. Number of particles are escaping at plus infinity. Okay. Now this is how the grand canonical OT problem and the multi-marginal OT problem are related. And again, there is a convexification happening. If you want, this is again a convex hull. So if you take the function which is defined, let me call it C hat, which is just Cn of rho if the mass of rho is n and plus infinity otherwise. So if I have an integer mass, then I take the multi-marginal OT problem related to that integer, and plus infinity if the mass is not integer. That now this is defined on the set of measures with no restriction on the mass. And now if you take the convex hull of this, then you get this C rho, which is the grand canonical OT. And this is written like this, of course, which is a bit more complicated, but it's the same thing that I'm saying here. Grand canonical OT is a convex envelope of multi-marginal OT defined in this way. So again, multi-marginal OT, so multi-marginal OT written in this way, so this C hat is convex in rho if and only if the grand canonical is actually canonical, right? So if this is actually convex in rho on these points, right, on the integer guys, then it means that C rho, which is the convex envelope, agrees with C hat of rho, which means that actually the grand canonical agrees with the canonical. So it means that actually the minimizer that I will find will have that I have a probability 1 of having n electrons. So it is not convenient for me having n plus 1, n minus 1, different number of electrons. I actually am canonical, okay? And of course, this is not so intuitive to understand if the grand canonical is canonical. The capital N, yeah, in this case, is the mass of rho, yeah. So we are thus interested in the support of P, where P is this probability measure on N, right? So when I will talk about, also when in our paper we talk about the support of the minimizer, we mean what are the number of electrons possible in the minimizer, right? And this is the novelty in grand canonical optimal transport. And now I don't have the time to do the proof. Here I just put the result for the Coulomb cost, which is the best result that we have. We have several results which are different for different kinds of costs, and usually we have just results for pairwise costs. Okay, so only Cn, which are sum of L, xi, xj. Okay, so something like this, but instead of having Coulomb cost, we have a general cost here. Okay, and here the natural assumption for C0 and C1 is that they are 0. Then for all finite and non-negative measure, right? So blah, 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 we have the support. So this is really, this P is actually the little p that I wrote before. This is in between these guys. And now this is what? This is more or less n minus constant square root of n plus constant square root of n. Okay, it's more or less equivalent to this. Okay, and in particular, this is saying that the interval here is actually little o of n, which is, if you wish, the important thing, right? Yeah, so in this case, yeah, capital N is the expected value. Actually, in the slide is rho of omega. So is the total mass. Yeah, of course. Yeah. It would be nice, but this is not saying that, of course, right? Yeah. What I would like, of course. Yes. And here you see this rho of omega is the expected value of electrons. And so I'm saying that I'm in this range. The only time where I know that there is just a single guy is when the number of electrons is 2. When the number of electrons is true, we can prove actually that there are only 2 electrons. There cannot be 1 and 3. is disadvantageous. Okay, so these are estimates from above. So this interval is less than square root of n, let's say, constant square root of n. What about from below? So do we have some counterexamples? Actually, yes. And the smallest that we found is this guy here, where we have that rho is the sum of Dirac masses in these 6 sites. And this actually also is quite nice. So it's this is a rhombus. This is 1, 1, 1, 1, 1, 1. And then we have this parameter t. So for a range of t, this actually works. And these are highlighted in red and blue are the minimal configurations. So which means that the best way to do this is not having 3 and 3, but it's having 4 and 2. Okay, in total, we have the average mass. So the total mass is 3. So the average electrons is 3. But the optimal plan is actually these 4 blue points and these 2 blue points for the grand canonical. So in this case, the grand canonical is different from the canonical. And so this is a counterexample for just 3. But now the beautiful thing here is that we can fractalize this thing. If we scale everything down enough and we put again in this point here, and then we do it k times, right? So we get this kind of fractal where now we have 6 to the k particles, right? 6 to the k particles, and we average them out. So we have a mass which is 6 to the k over 2. And actually, the support is precisely these 2 guys here. So either we have 6 to the k minus 2 to the k over 2 electrons, or 6 to the k plus 2 to the k divided by 2 electrons. Okay? And this is just because, so let me see. Okay, I cannot say it very briefly, but iteratively, you can show that this should be mainly blue, this should be mainly red, and actually then you choose here again the pattern which is correct, and so on and so forth. So now this is not square root of n. So this is the interval which is long like 2 to the k, and the n, so the expected value is 6 to the k divided by 2. So it's not the square root, is a power alpha, where alpha is logarithm of 6 logarithm of 2 divided by logarithm of 6. So it's an exponent alpha. So we have a counterexample. This is saying that we have a counterexample like this with n as big as we want, basically. Sorry? I don't know if I written somewhere, but logarithm of 2 divided by logarithm of 6, this is 0.4, if I'm not... So it's between 0.3 and 0.4, something like that. So it's far away from 0.5, but also very far away from 0. So it's not constant, this guy. And so we were very satisfied with this. It would be nice, of course, to close the gap and to arrive at least at the exponent which is the same. And in order to do so, of course, with this strategy of fractalizing is sufficient to have one example with a small number of atoms for which this is actually the square root. So we have really the square root, and then if you fractalize it, then you will obtain, yes? Yeah. Yeah, I don't think so, but yeah. I don't know, but I guess that you can tweak a bit this example to get everything in between, 6 to the k and 6 to the k plus 1, right? I'm not so sure, but I guess that this is true. So if you want, this is a conjecture available for everyone. Okay, coming back, and I'm finished. So again, we needed to see whether if these two are equal. So the conjecture is saying these two are equal for every v. And now, as I was saying, this is saying that E is the dual of F, EGC is the dual of FGC, but it's also true the opposite way around. So F is the dual of E, and FGC, sorry, is the dual of EGC, and F is the dual of E. So actually, we can prove that equality holds for every integer n and for every v. I didn't write it. If and only if FGC is equal to f of rho for every measure with integer mass. Okay, this is just because one is the dual of the other. Okay, but then this is saying that we have a counterexample to convexity of the energy, and this counterexample actually you can take the counterexample that we have there and try to come up with the counterexample for the V, which is the counterexample for this one, and you basically take the potential, the Kantorovich potential associated to this one here, which actually is very strange because it lives just here, 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 and here, and is like minus infinity otherwise. So in order to tweak it, actually you put potentials which are like this, so they are going to, sorry, they are going to plus infinity. No, it's the opposite way around, because the sum of the potential is less or equal than. So it should be like this. Yes, you have to put potentials like this in every point, and then scale it out then in order to add again the kinetic energy, because this is now without kinetic energy. And so the counterexample that we have is actually with a potential which is coming from small fractional charges in these 6 sites. So basically we have V, which is coming from 6 atoms, but these atoms have fractional, very small charge. It's like 0.02, I guess, something like this. Why is it small fractional? Because going from this to adding kinetic energy, we have to do scaling, and this scaling is so you are paying both in scaling dimensionally, right? So they are going far apart, but you have to scale also the fractional the charge. And so the charge goes like how big you are, and it's something. Yeah. It's only relevant for epsilon greater than 0, which is the real physical question, if you want. And so we have this fractional charging in 6 sites, and of course it would be nice to have the counterexample. So the still big open question is to construct an example with a potential coming from integer charges somewhere, because this would be a physical counterexample. Because up to now this is not physical because you cannot construct fractional charges 0.02. Okay, thank you for the attention.
Thanks,
Sorry,
Simone. Is there any question? Please.
Thank you.
Yeah, congratulations for the very nice result. So I was wondering on the putting back the, I mean, turning the Coulombic example into one with the H bar non-zero. So why can't this just be done by a little modification of the charges into, you know, like a small Gaussian or something like this, and then do the usual low density scaling that turns a sort of real system into this epsilon equals 0 limit? Because as soon as you take a convolution of this delta function charges with, like, say, a small Gaussian, you get finite kinetic energy, and as soon as it's finite, you multiply with a small epsilon, so you should get it for a small epsilon.
So I don't know. So the problem is I have to look it again, but I try to understand that. I think that the problem is really that you need, since this is something at the second order, if you want. So it's a correction and at the next order, you need always the scaling also of the charges. And so I'm worried that also if you do like this, the total charge will be fractional as well, and so it cannot be again like this. Also because I guess that in the proof at least we use also that the charges are smaller than one, in a way that every site can bind no more than one electron. So in total, we need to have no more than 6 electrons. So I guess that for now, for how we did it, that there is no no more wiggle room allowed for now. But maybe with other examples, with other counter examples to the convexity of to the optimal transport grand canonical equal grand canonical, maybe one can find a way.
So I have a question. So in DFT,
Yeah.
most of the what people call approximating models, like Thomas Fermi, von Weizsäcker, what Lieb denotes by D of rho, they are all convex. So your result means that they are not reliable for the reality, or what?
So actually, they are not always convex. So for the example, the LDA is not convex, I guess. So there are counterexamples
Yeah, but
also
most
for
of them
that.
are convex.
I guess that most of them are convex. Yeah. But there are many problems with the approximations in general. Of course, this is saying so. Of course, the whole story is understanding. So let me just come back to this slide. I could write like I don't know 100 slides like this, meaning that all the relevant examples, all the examples that were found experimentally, numerically, etc., they are all convex, right? So maybe every physical expectation is still convex. So it's something that really we quite so it's not clear what is happening actually. So even when we were looking for the counterexample, so if you so we looked for the counterexample like this for I don't know, for maybe more or less 1 month, 1 month and a half, and at the beginning was just numerical computations, because it's like 6 sites. You take 6 points at random in I don't know 0, 1 times 0, 1 times 0, 1. You paint 6 points at random and you see if grand canonical equals canonical. And then for 1 month and a half, everything is canonical, right? So it means that actually the probability of getting something which is non-canonical is actually pretty small, right? So looking for this, and then once we tried some geometrical configurations, and then like after 2 or 3 days we found this. It was like, okay, nice. We don't know why, but it works. And so this is something that so one thing that I'm interested in actually is to understand how many configurations and how this scales with n with the dimension, because now this is in dimension 2, but maybe in dimension 3 there are more, maybe there are less. It's not clear. It would be interesting to understand what is the, I don't know, the worst best example or something like that. So it's not clear.
Okay, let's thank Simone again.
Okay.
Oh, what? Sorry.
The lattice here is 2 dimensions, but it's the 3D Coulomb potential. Is that right?
Yeah. But of course, this can you can put it in 3 dimensions as well.
Right. But you didn't look at logarithmic potentials or other Coulomb potentials for other dimensions. I mean,
No.
Okay.
No, because actually, so I didn't say the full story. So I mean, the full story is counterexample existed for different kind of potentials. So if you take the interaction potential, now in calling the interaction potential, so Lib in his first work came up with the counterexample with the interaction potential, which is 0 plus infinity, something like that. Again, some geometrical construction not similar to this, but then that was reprised like 2 years ago by Ayers, which showed that the same configuration actually works for every power law with the exponent which is bigger than 1.43, something like that, which is, I don't know, logarithm of 2 or something like that.
Yeah.
Right? So in this case, and this of course works from dimension, I don't know, 4 and on. But this does not work just for Coulomb so the counterexample by Ayers didn't work just for Coulomb in 3D. Works for Coulomb in 4D, etc. But we didn't look at this because there was already some counterexample. The one that was missing was Coulomb in 3D. So this is why I focused on this.
Thanks.
Okay, thanks again.
Thank you.
Simone. Okay, let's proceed with the third speaker, who is Guillaume Carlier from Paris Dauphine. And he will speak about sharp comparison between the one Wasserstein distance and its sliced version. Please, Guillaume.
So thank you very much, Giuseppe. And first of all, I'd like to thank the organizers. It's, as usual, a great pleasure to be back to Pisa. Not as a veteran as Jan, but still, it's at least I've been a regular visitor. It's at least 20 years, so it's really nice to see old and new friends. Old and new is a common expression here. Okay, so I want to talk about. I'm doing a full Blackboard talk. I suspect it's the first one, right? So traditions have changed. So I apologize in advance. My writing is terrible, as students say, but I'm in love with blackboards, and I know that Scuola Normale Superiore has nice blackboards, which is not the case in French universities anymore so much. And so I'd like to talk about a comparison, some comparison results, quantitative comparison result between Wasserstein distance and in fact the one Wasserstein distance and its sliced counterpart. And it's a joint work with Alessio Figalli, Quentin Merigo, who is here, and Yi Wang, who is a colleague from Johns Hopkins. So don't look for a preprint on archive. We've been quite lazy or busy in the last months. So we're confident that something will be posted maybe by Christmas or slightly before or slightly after, depending on random shocks that will affect all of us. So let me explain a little bit about the setting and the motivation. So I will work on RD, and I'll mainly consider the case of measures which are compactly supported on some ball of radius r. So r is a typical size of the problem of the data I'm interested in. So I'll consider mu nu probability which are supported on BR. And I'll be interested in the one Wasserstein distance between those two guys, those two probability measures. And, well, you know from the Kantorovich duality formula that can be expressed as a soup of phi d mu minus nu. But so W1 is a bit special because it's semi-norm, the Lib prime semi-norm, it's invariant by translation, which other Wasserstein distances are not, with phi one Lipschitz. And in fact, you can also restrict yourself to functions which are one Lipschitz defined on the whole space and which vanish outside, let's say, of a ball which is, let's say, 3 times the radius. you can also assume that it's defined on the whole space, and they vanish outside, let's say, let's be pessimistic, outside a ball of radius 3r, right? You take in convolution with the distance you normalize the potential so that at the ball the maximum is 0. When you convolve the distance, you become positive outside of the ball of a sufficiently large radius, and you take the negative part, and so a counter-H potential can be taken to be compactly supported. So this is quite a common object, of course, in a NOTI conference. You all know about it. But the point is that it's quite costly to compute or to evaluate in large dimension, but it's very simple in 1D. Because in 1D, there is a closed form formula. In fact, in 1D, the one Wasserstein distance, if D equals 1, is just the L1 distance between the CDFs, okay? So F mu are just the CDFs of the measures. So there's a very close form and simple formula. And given this, it's very tempting to slice the problem. I think it's an idea that goes back to Marc Bernold. It was more than 15 years ago. It was around 2008 or something like this. And Marc Bernold proposed, it was around, I don't remember, according to Jan, it was 2007 or 2008. Filippo, it's fair to say this. So Marc Bernold proposed the sliced variant, okay, which only involves projection or 1D marginals of mu and nu, and the sliced Wasserstein distance between mu and nu is just the average over the sphere of the one Wasserstein distance. Now it's in 1D. Mu theta and nu theta are just the marginals, the marginal in the theta direction. So mu theta is just a push forward of mu by the theta component, if you want. So there is a closed form formula, so it's not very difficult to compute. Okay? But now, so there are a few observations. The first one is that, of course, since these projections are one Lipschitz, it's clear that SW1 is controlled by W1, right? It's quite obvious. The second observation is that both, actually SW1 is a distance as well. You can see this using a Fourier argument. I'm going to use a lot of Fourier arguments in the sequel of the talk. Well, so, okay, these are both are distances, and in fact, both metrize weak star convergence, okay, on the ball. So in fact, they are topologically equivalent. So from a topological point of view, using one or the other gives you the same kind of, metrize the same convergence. But now the question, what about, so they are topologically equivalent, but what about metric equivalence? So you can convince yourself quite easily that in fact they are not metrically equivalent. To see this, I'm not going to get very much into the detail of an example, but you can convince yourself even in 2D. So think of mu, which is uniform on, let's say, an horizontal segment. Okay, and now take some approximation, call it, let's say, nu epsilon, which is uniform on a thin rectangle. Okay, I mean that the width here is of order epsilon. Okay, so you can convince yourself that the Wasserstein distance between mu and nu epsilon is at least of order epsilon, because of course in the vertical direction the displacement is typically of order epsilon. So clearly this guy is larger than epsilon. But at the same time, the horizontal projection is the same, and in fact, except when you're very close, when you integrate of the sphere, unless you're very close to the vertical component. In fact, the order of the one Wasserstein distance is more or less quadratic in epsilon. Okay, of course you have to remove a small neighborhood of the vertical component to see what's going on. But when you do the computation, when you compute this, this is more or less quadratic, and maybe there's some logarithmic correction like this. Okay, so from this you see that this is not of the same order, and if you look for a comparison in terms of a sort of older comparison, in 2D, the best exponent you can get is 1/2. Is it clear? Okay, so they are not metrically equivalent, and there should be some restriction on the kind of quantitative comparison you can make. I'd like also to mention there is a theorem which is really nice in this direction, which is due to Nicolas Bonnot, and it's a pleasure to quote after Marc Bernot Nicolas Bonnot, because again, a very original and very clever young researchers who actually did his thesis with Luigi is not here, right? Is he? And Filippo, and left academia to go to work in the industry. And Nicolas proved it's very nice. It was, by the way, it was unpublished, but it was about slightly more than 10 years ago, if I'm not mistaken. It's in his PhD thesis. And Nicolas proved that there is a constant such that the Wasserstein distance can be, so it's a dimensional constant if you want, is controlled by this constant times R, the size of the data, which is this time Wasserstein distance to the power 1 over d plus 1. And of course, I made a mistake here. It should be d divided by d plus 1, if I'm not mistaken. The total homogeneity should be 1, right? This is if you scale the problem. Okay. And so now the question, so there exists this result. It's quite, seems people are, it has become a quite popular object, these sliced distances. But you can see this as a kind of surrogate of the full Wasserstein distance. How reliable it is. You see that 1 over d, sorry, I made a miss. Oh, sliced is here, sorry, the S is missing here. Yeah, sorry about that. Sorry. But you see, it's of the order of 1 over d. So it deteriorates with dimension. So it's not very reliable. If this exponent is sharp, this is not really a good news in terms of using sliced as a good surrogate of sliced Wasserstein in terms of Wasserstein in high dimension. So the question is this exponent sharp? And can we improve the result of Nicolas? And the result is the following. So let me stay. Yeah. Sorry. Yes. Which one? Okay, so where? I don't think I can improve the light, right? But I can improve the exponents. Maybe you don't care. Okay, so the main result is the following. So here is the theorem. So Alessio, Quentin, and Yi. Of course, it's not going to be very impressive. I'm going to improve the 1 over d plus 1 to the 1 over d, more or less, up to a logarithm factor. But the point is that we have an example which shows that this is sharp. So improving if you want to prove sharpness, it's nice to improve a little bit the exponents so that you reach the sharp one. So same results. That okay. What we could prove is the following. Same business. So RD, compactly supported measures, the size of the data is of order R in RD. And there is a constant such that we can improve the exponent to So it's r to the d minus 1 to the d. It's the right scaling SW1 to the 1 over d. This is for d, which is odd. And in fact, in even dimension, we could not exactly prove this. There should be a logarithmic correction. I will show you the proof. So if d is odd, and if d is even, there is some log correction. So it should be something like SW1, log of something crazy, which is 14r e2 to the SW1 between mu and u to the 1 over d, if d is even. And the key point is that the remark, 1 over d is sharp. You cannot improve this exponent. We have an example which is a refinement. It works in another dimension of the thin rectangle example. It's quite involved. I'll not give the details. It takes a few pages of computations to justify. You need the approximation is not by a uniform measure on a thin rectangle. It's something more subtle. You have to cook some weighting in the orthogonal dimension with a lot of oscillation to kill many terms to reach the 1 over d exponent. 1 over d is sharp. Maybe the log is not in any dimension, and maybe the log is not. The log might be an artifact of the proof. But in fact, it's not even a log, right? It's a log to the 1 over d, so it's harmless in large dimension. But if you know of a way to get rid of this log, come with a better proof, would be happy. There's no t, that's e. Okay, it's e2, and yeah, my writing is terrible, but my e looks. It doesn't look like an e, but it doesn't look like a t neither. So, sorry. Right. So now I want to give you an idea of the main ingredients in the proof. And of course, maybe the main result, and I mentioned maybe some variances 5 times in the end. Yeah. And maybe the important stuff is that we were able to find an example which shows that this exponent is really, you cannot beat the 1 over d. So the example is more it's more generic. In any dimension, you can find something of the same kind. Okay, am I clear so far? Yeah. Okay. Is the next speaker using the blackboard? Oh yes, tomorrow. So you don't care, right? Okay. So let me give an idea of the proof. The idea of the proof is the following. So first of all, let me regularize the first step, maybe, or step 0 is to regularize a bit the data. So let me take some scale, which is of the order of r, let's say, some lambda to be fixed later. Let me take a modifying family. So rho lambda is 1 over lambda d, rho lambda, where rho is a smooth probability measure, which is probability density, which is supported on the unit ball. Okay, and let me convolve mu and nu by this kernel. So let's look at approximated smooth versions. And it's, yep. And okay, so they are supported typically on the ball of radius 2r. And let me take phi to be a Kantorovich potential for between mu lambda and nu lambda. So if you do so, first of all, you can evaluate, you want to control the Wasserstein distance. Okay. Of course, by the triangle inequality, there's a price of regularizing mu and nu, but it's of order lambda, so it's less than 2 lambda. And then you'd like to control the Wasserstein distance between mu lambda and nu lambda. And this guy is the integral of phi mu lambda minus nu lambda. And you can pass the convolution onto the Kantorovich potential. and you're back in evaluating this guy, which is now globally one Lipschitz, super smooth, and also compactly supported. On a ball, let's say, of radius, if you 7R or something like this, that's why the 14 was coming from, but it's very pessimistic bound. Okay, so this guy is globally one lip, it's smooth, and it's compactly supported. Okay, the size of the support maybe, it's of the same order as R. So now you see the game, you'd like to represent this smooth guy as a superposition, to see where the projection appear, you'd like to represent psi as a superposition of function of one variable. Okay, this is a classical task, for instance, in when you try to invert the Radon transform. In integral geometry, this is a kind of things, recovering a function of several variables in terms of its integrals over planes, for instance. So this is the second step. Step one. It's represent psi, this nice function, as an average over the sphere of a function of one variable, right? So typically, that's what you do. It's very tempting to use Fourier transform to do this. So you write the Fourier inversion formula. So psi is as nice as the function as you want. It's smooth and compactly supported, so it belongs to, in particular, it is a Schwarz function, so it's really nice. So psi, you can write it as the integral of the Fourier transform to the exponential of 2I pi xi dy, okay, on the whole space, on RD. Now you write the Fourier variable. Yeah, am I Giuseppe with something? Yeah. Ah, it's too. But can you read the yeah. Well, maybe the color is not optimal, right? I should use white. Yeah, thanks. Sorry about that. Sorry about that. Yeah. Okay. And then you pass to spherical coordinates. So up to constant, this is the same as the average of the sphere, over the sphere of the integral on R plus, or of psi hat, you write y as r theta, exponential to I pi r theta x, r d minus 1 dr d theta. So from this, you see that if you set psi theta t is precisely the integral on the positive alpha line of psi hat r t theta e to the 2I pi r. So t becomes theta x, rd minus 1 dr. You see that this family of function of one variable does the job. So by definition, psi of x is the integral of psi theta. There's a constant. Okay. Now we'd like to understand what this guy looks like. We are kind of reinventing the wheel. These formulas are well known. A little bit of sport. But for those of you who are not familiar with Radon transform inversion, I want to show you the computation. So I have to understand what this guy looks like. Then I have to understand what the Lipschitz constant of this guy uniformly in theta with respect to the t variable looks like, and to plug it in my first inequality and try to optimize to see that the order of Wasserstein 1, okay, there is a trade-off. I have to optimize in lambda some quantity, and I want to find that in the end, it's of the order of slice Wasserstein to the 1 over d. That's more or less the step, so it's quite natural kind of proof. So, okay, I'm not happy with the rd minus 1 factor, so I can write psi theta as a d minus 1 derivative in the t variable, and there's a prefactor which is here. That's just to get rid of the rd minus 1 factor. of this guy. And now you see where the case where d is even or d is odd is going to play a role, because you see this factor has I to the d minus 1. So if d is odd, you know the prefactor is real. Of course, this function is real. So you can take the real part in the inner integral, right? You can take, so the prefactor is real. And you can take the real part in the inner integral, in this one, before differentiating, right? In the inner integral. But it's very nice, right? You're adding the missing part. You take the conjugate, so the part which is not present here, so the integral on the negative half line is showing up, and there's a 1/2. I forgot to say that there's a dimensional constant all over the place. Okay? And then, again, so not again, but it becomes the derivative up to a constant of, it becomes a full Fourier transform. And now there's something well known about this guy. If you fix theta, this guy as a function of R is a Fourier transform of what is called the Radon transform. So it's a consequence of Fubini if you want. So the Radon transform of psi as a function of one variable theta is the integral of psi on the plane whose equation is theta scalar x equals t. So you can write it in this way. It's the integral of psi of theta plus z, where z, so pay attention here, the measure is the d minus 1 measure on the orthogonal of theta. And it's easy to check that the Fourier transform of the Radon transform in direction theta of this guy st is precisely, or let's write that R, is precisely this guy. Okay, it's called the Fourier slicing property or something like this, but it's you just use Fubini's formula in the Fourier transform, in the formula for the Fourier transform. So this just this guy. So you see, this becomes Fourier transform with this guy. So you Fourier inverse again. So by Fourier inversion, the guy which is here is just the Radon transform evaluated at t. So then you discover that the function, this guy is just up to a constant. It's just this operator for integral geometry, so integral of the initial function on plane, but you differentiate d minus 1 times. Okay. But if d is even, the prefactor is purely imaginary. So it's not the real part that you have to take. It's the imaginary part. So then the missing part comes with the minus sign. So what you have, so you have to take the, am I clear so far? Yeah. You have to take the imaginary part in the inner integral, right? It's not really a big deal. This guy taking the imaginary part becomes the integral on the whole line, but there's a sign change, okay? So it's a plus on R plus, but it comes on minus on R minus. So there's a symbol which shows up, which is minus I times the sign. Let me denote the sign function like this way, but otherwise, it's still the Fourier transform of the Radon transform. So if you want to use the Fourier inversion here, it's fine, but you have to declare that this guy is a Fourier transform or something else, which is a so-called Hilbert transform. Okay, so this guy is so this is a special, quite well-known operator. It's the first example of Calderon-Zygmunt singular operator that you're facing. So this becomes the so-called Hilbert transform, which, by the way, is defined just as you want. So the Hilbert transform of a nice function in Fourier is just the Fourier transform multiplied by this symbol, minus I sign. And why do you take? Why do you have an I? Exactly because of because the sign is a not function, right? And okay, so this is called the Hilbert transform. And there's an alternative expression for this, for the Hilbert transform. More or less, it's a convolution with the borderline, non-integrable, but almost kernel 1 over x, not 1 over modulus of x, but 1 over x. And since it's not integrable, you don't define it as a convolution, but in the sense of Cauchy principal value. So you can define h phi. So it's in 1D, right? Now it's R is in 1D. The Hilbert transform can be defined as the limit as epsilon. Phi is a nice function, okay? Of the you remove a little bit a small neighborhood of the origin, and you integrate phi t minus s divided by s ds. Okay, that's the idea. But what the Hilbert transform looks like. It's a non-local operator, and at some point we will have to face this. So in this case, the function psi theta t, from which you represent psi as a superposition of function of one variable, it's the same as before, but with a Hilbert transform. And Hilbert transform is translation invariant, commutes with derivatives, so you can put inside, outside, doesn't really matter, right? So the same as before, but with this singular operator here, right? Okay. So let me maybe, this is 1, this is 2. So let me conclude. I have 5 minutes or 5 minutes, yeah. Let me not conclude, but explain the easy case. So step 2, it's proving the result in odd dimension. So step 2, end of the proof for the odd. For the odd, then remember, I was to control the Wasserstein distance between nu lambda and nu lambda, which is now it's a double integral, right, of psi theta, which I integrate between. So the function, the Kontorovich potential convolved with the kernel. It's important to justify that its operations are well defined and so on. It's nice to have some smoothness, and compact support is also convenient for when you have singular integral operators, which is not the case in odd dimension, but for the even dimensional case, which will play a role, d theta. Here you see that this is Kontorovich-Rubinstein, the Lipschitz constant times the 1 Wasserstein. By the way, Kontorovich invented Wasserstein distance for that purpose. That's why it is called Wasserstein, probably. And so this is less than 2 lambda plus the sup of the theta of the Lipschitz constant of psi or theta times, when you integrate this guy, you precisely as sliced Wasserstein. So we have to understand what the size of this guy. Of course, it depends on lambda, right? Okay, I didn't want, there's theta, lambda, and so on. So, but psi depends on lambda in 2 ways. First, I took a Kontorovich potential associated with regularized marginals, and then I convolve again, okay? But, okay, remember that, in fact, to make a long story short, what you can prove is that the Lipschitz constant of psi theta, which is compactly supported, you can prove that since it is, yeah, you differentiate once, you pass one derivative. This is the point that Bonnot was missing, actually. The fact that you start with a 1 Lipschitz function, there is one derivative which is for free, which is of order 1. So in fact, what you can prove is that this guy is less than a constant times lambda to the d minus 1. Okay? You could say, I'm differentiating d minus 1 times because of inversion, and once more because I want to estimate the Lipschitz constant. In fact, it's not true because you started with a 1 Lipschitz function. So if you do this, you see that Wasserstein if of order lambda plus 1 over lambda d minus 1 times SW1. So you kind of optimize or just equate these guys. So you choose lambda, which is the order of sliced to the 1 over d, by the way. So those two terms, which by the way is of the order of r, okay? And then you get the results. W1 becomes less than SW1 to the 1 over d, and there's a constant, there's a dependence in r, but there's a natural scaling invariance, so the dependence in r should be r to the d minus 1 divided by d. Okay, so it's the end for the odd case. Do I have Giuseppe? Yeah, okay. So what I want to say, and I won't get into much details, but there is an extra log, at least with this proof. Maybe there are better, smarter decomposition of one Lipschitz. What is nice with this decomposition is that you can control somehow the Lipschitz behavior of the psi theta, at least when d is odd. So step 3, you have to dig a little bit into the dirt, if I may say so. The point is that you have to take psi theta becomes h of the same guy as before, something which is roughly 1 over lambda to the d minus 1 Lipschitz function of one variable. But the first thing you learn from the Lipschitz transform, it's a linear continuous operator from LP to LP, but it's not linear, it's not continuous from L infinity to L infinity. It does not map, it maps Sobolev function to Sobolev function, but not Lipschitz function to Lipschitz function. So it's typically something which behaves like an absolute value near 0. It looks like an absolute value log. Okay, that's the key point of this singular operator. But the nice thing is that in fact, H does not map compactly, Lipschitz compactly supported functions to Lipschitz functions. But to log Lipschitz ones, it's kind of a borderline case. The borderline integrability of the kernel, the price you have to pay, well, it's always like this, right? It is a log, but it becomes a log Lipschitz function. And it's quantitative, right? There is some constant, but it's totally explicit, okay? So that's why, in this case, I don't want to get into the details, but you cannot, okay, here, you cannot write this because this you cannot control, but the trick is to change the distance. You introduce a new distance, which is not like, it's not the distance on R, but which behaves more or less like distance log 1 over distance. It's still a distance at a certain scale, okay? And you use Kantorowicz-Rubinstein, so Lipschitz becomes the log Lipschitz constant, and you do the same business. The price you have to pay is that here you don't have Wasserstein 1 for the usual Euclidean distance, but for this modified distance. And when you do the computation, you arrive at the kind of bound I propose, which is 1 over d up to a logarithmic correction. Okay, so okay, yeah, I think my time is over. If you have questions, maybe you can discuss about some variants and so on. We also have results where instead of looking at marginals on, we lose a lot of information on projecting on lines, we project on higher dimensional planes. So we have similar results, but the kind of techniques are the same, slightly more involved, because instead of having derivatives, you've got fractional Laplacian, which shows up. Hilbert transform is replaced by Riesz transform, and so on. But basically, the same kind of arguments are the same. And thank you very much for your attention.
Thanks, Guillaume. Any question for Guillaume? Please.
Speaking of variants, so what if you replace W1 with W2, for instance? Is there? I thought that would not actually work with W. I mean, maybe I don't recall it correctly, but I mean, the estimates are there. Of course, you don't have any more the Lipschitz, you know,
Of course, you can deduce something from W2, and okay, but using Holder but you lose the exponent. But probably we lose we have still an inequality, but probably you lose the optimality of the exponent. And probably this serves, and we have some strategy, but so far we have no clue about what the exponent behavior should be because if for general convex cost, right? Here it takes no time. There's no time involved. You don't have to go through Hamilton-Jacobi, but Hamilton-Jacobi and this business of yes, but then you can use this and control. Okay, of course, there's W1 by W2 and W2 but you lose an exponent. Probably the exponent you get using order once, you lose sharpness. That's our guess. So we don't know yet what the sharp exponent would be and what is the sharp technique we should adapt to this case. And also the examples plays a lot with the fact that we have to make a lot of oscillations, we have a lot of cancellations to reach a slice which is of the order epsilon to the dimension in this kind of example. It's really translation invariance is quite important as well. So that's a very good question, but for now we don't know how to answer it sharply.
Filippo.
I was wondering whether the fact that you use in the proof at the moment is derivative to power d-1 is related to this surprising result by Slepchev about the fact that in the slice, the vast time flow, you have an operator which is morally of order d or d-1. So he has also some higher order derivatives which are involved in slicing.
Yes, I think so, right? And I think this step 2 is kind of folklore, I forgot to say, but and I think in the paper of the Jan, there's an appendix where all this inversion formula plays a role, I recall, and so on.
Here it's quite clear. You write an integral and then you write it is the other,
yes.
In the fact that...
I would say so, but I cannot answer very sharply, but I think that this is a very same reason. You see, that's a representation. But the point for the sharpness, there might be, it's convenient to use this, which is a tool which is well known in integral geometry. But maybe there are smarter decompositions for which maybe this singular operator does not show up, right? You use Fourier because that's just laziness, right? But maybe if you're not lazy or...
Can I ask one more question? Yeah, so there was recently a nice not generalization, but variation on slice assertion that was proposed by Laetitia Chavel. So what she says is that instead of summing the 1D distance, what you do is you look at the plan, so it induces the transport plan between alpha and beta, and then you directly evaluate on the original space the value of the plan. So it gives you like a candidate for a transport plan. So it's a way to somehow upper bound the Variation slice distance, which is not the case with slice because slice is not an upper bound. So I'm wondering whether you think this type of idea, where you compute a suboptimal plan by a 1D projection.
I don't think it would work because, okay, I forgot to say, but...
I mean, the question is whether it would give a sharper bond than this.
Okay, the answer is probably no.
There is a meta theorem that says it's not possible.
Okay, that's a good question. Maybe I got the construction you suggested wrong, but maybe you lose something by taking the average over the sphere. You could take the L infinity, the max slice or something like this.
She used the mean. She used the mean. You provide an upper bound and she used the mean.
Okay.
It's not max slice. Max, you max over the 1D distance. She mean.
Okay, but do you mind if I try an answer? Maybe it's not the right one, but if you use max as an upper bound, the best exponent you can guess is something between 2 over d plus 2 and 2 over d plus 1. Even for radially symmetric data, we have example where you improve the exponent by 2. Okay. No, but in the radially symmetric, we have example for the radially symmetric case where, in fact, everything is super rigid, where the exponent is still decaying in 1 over d, or in fact 2 over d. So I suspect, I don't know exactly what is the construction you suspect. Okay. So say it again, then maybe.
The original space. So she minimize instead of maximize. So she minimize over transport plan.
But in the world problem, so
on the original problem, the transport plan are computed by being a 1D transport plan. So she minimize over theta 1D transport plan. This defines a distance.
The minimum.
Okay, let's discuss after.
Well, let's discuss after, because if the maximum can Okay, maybe there's some misunderstanding, right? Okay. No, but I think there are similar abstraction. You can. I think it's affected by the curse of dimensionality anyway, and the fact. But did you listen to my answer? I said that the max cannot control very well the average. So, but the mean is even worse. The mean is even worse. It controls less. But okay, maybe I got it wrong.
A last question, Baghero.
Yeah, maybe. Yeah, very nice decomposition. So if we go back to your Fourier decomposition, so you basically can exactly write the original function as a superposition of sliced ones, and so then one wonders if you can you introduce a kind of weight in the sliced Wasserstein distance to recover something that has the right scaling with respect to the right W1 by just putting weights?
It's a very good question, but I don't know if these techniques have to do it, right? That would be also tempting to look at instead of having sliced, having a foliation and so on. It's not the same as you say, but then Fourier transform is not good for that. For probably wavelets or yeah, maybe. So there's probably, but the technique should be quite different. That's a very good question, but we don't know how to handle this apart from trivial scale. And probably I didn't understand the question of Gabriel, so I'm still puzzled, but
Okay, so let's thank Guillaume again.